okay? Well, we don't have power, but it's okay because we have voice technology, translation technology.
그래서 달로민도 저도 들었는불라 아니 임비는 만줄라 케키 아니 다 주제스야 되다 다 유래기 아니 주제스야 돼 단다 하디요레스.
And we light a candle. Buddhism lights a candle against the darkness, and science also makes a light against the darkness.
그래서 다 먼저 될라 주메지 파르셔 요레스 나중에 그 나로라 다 지금 마릭 문바세야 다 데베 토라 다 주메드 남규 아니 선도 계신 모습이 요레 대가나신 세력 나로를 임비나 아니 다 만통의 그 문바세와라 아니 왜 배주치기 요레스.
I'm going to talk about how we know what we know, not about the knowledge itself, but how we gain the knowledge.
그래서 당에 계제시야 조 가르치기 요레스라비면은 아니 간주기 아니 가르치신 받은 조 가르치 요레스야 디자마이바 가르치신 받이 컨디션이 셴바레스야 조르와 디골 아니 계제시그레스.
And I could and will talk about the basic of the scientific method, observations, hypotheses, theories.
그래서 다 디시 좀발라 지나 안에 시리 도단 배차시는 당봉년라 안에 내주직 독식 중요 안에 되네 안델라 안에 가리 이메게 처바 지야직다 안에 데 딕도민도기 안에 저 무스탁지 지야 다 딘주기 도림시기스.
But I also want to remind you that science is a very human activity, and science involves luck and intuition, and it's highly creative.
그래서 임비나 전수 제고야 지라 안에 세력스야 돼야 안에 로미기 안에 자주지 차디 요레스 그래서 디인도 잠발라 안에 지금 소소수 게르기 안에 삼로타야 단데베기 니즈 망보시 디나라 추디 요레스.
Too many people, especially those who think science is maybe threatening or a little intimidating, consider it something separate, something that they have no access to.
그래서 안에 미카시 요레스 가 디나로는 조 카시 그 세력 수비 삼발라 지 닝가지 고올은 진드니 키미딘데 요레스 그래서 딘조 미딘조 응을라 안에 세력라 직다 소소소다 데와 메베 소로 시제 안에 타링산 데데야 데네 직차기 요레스.
But every one of us is a scientist because when we are born with curiosity.
이미나 우연히 줄은 아주 상만 세력과 차대 요레스 먼저 기준이 고라 안에 먼저 삼로 그 나로라 안에 직다 도주스 이루어져서 되게 아니 다 가리나 삼매기 아니 삼로 땅다직 돈 냠돌레디 요레스.
The smallest baby is looking for patterns, is interpreting data from the natural world.
그래서 부충쇼된서 임베임베나 아소소기 코리오 그 나로라 아니 직 패턴 세두 삼바 아니 코리오 그 나로 고림기 내단 가르도 된서 아니 고알랭아 기탑시 제디 요레스 제자 딜라두 삼발라 라운중 코리오 그 나로라 아니 지도 가리오와 디 아니 따디 요레스 고랑기.
Scientists are doing exactly the same thing, except with more sophisticated tools of technology and mathematics.
그래서 안에 세력 봐주기 내가 대가랑 제디기요레스 임베나 콘소기 직다 앙지다 아니 주제 고뇨와데 배주 제약이 제월 삼지 요레스.
So the first topic, of course, I want to talk about the ways we see the universe. I will use cosmology or astronomy as my example, but what I talk about refers to all branches of science.
그래서 안에 당봉에는 예시도 삼발라 안에 간주 가래 통구요와 딜라시 샤제 아니 계제시 그래서 제다 아니 가른 통화 실을 샤제 셔야 된 세닉 찔라 차버지 레든 이미랑 예 조디 조소다 가지 릭발라 아니 페샤제 아니 시그레스.
So the first thing we have maybe is vision, the most obvious and the most powerful human sense.
제가 안에 당보들 간주 소통토베기 아니 다 미기 왕부도 요레스 제가 다딘 로미기 아니 왕부 나로네 다 네바 제슈도 차디 요레스.
We learned a lot about the universe simply with vision. Long before the telescope was invented, Greek philosophers used observations of the sky to deduce important things about the universe.
제자다 양시 사드 마지베 응외네 간주 기타 미기 통야 디zamla 배제 제베 또는 간주 내주 망부지 간주 감근앙로 도시 중요레스 그리키 냐마 따좀 켄트기 아니 지게 미기 배제 제베 또는 따랑중기 아니 도시 망부지 도스마 또르케 또 중요레스.
They were able to deduce that the moon was perhaps a world in space, the approximate size of the Earth, and some were even able to speculate that the Earth was not the center of the universe.
제가 군주기 따미기 도시 지어 딜레 시샤지 아니 직 배차신 남로 여베기 아니 직 다와도 신베나 아니 다와서야 디 아니 고 사신바지 임바다 살링신 링 신바지 임바 디기 체중야 아니 잠불링기 체중 삼지 여와 딜레 계자시 디나니 카시기 아니 직된 감나로 여베 가지고 기타 링디 가지고 잠불링 잠 임바 링 신바 여베기 아니 저바진이 중요레스.
In 1609 we have the telescope and Galileo's first observation of the sky.
제가 직동 두개 규미고 구글로 간주 단다 장시 통마도 소요래 제가 아니 갈릴레오 고랑기 장시 배주 제제 아니 다월 때 여러was.
The first telescope, very simple, Galileo's best telescope, the lenses are just this size, the size of a coin. And we actually, for the first cohort in Science for Monks, they got modern version of Galileo's telescopes to use at the workshop.
그래서 다 갤릴리오 코란기 표주체에 그 장실 된소 장실 답디 시우디는 차도 요레스 장실 낭로를 표주체에 그 당실세에 그 시고디 아니 제중 단다 아니 잠가 디금스 지미시 요 마레스 제가 딜레지 토네 아니 표주체네 아니 다 야르지신데 뭐 세교를 대가나신 안중님마 아니 세릭 sabju 유니키 아니 데젠 당부 게 아니 긴두 바솔라 아니 단다 갤릴리오 게 아니 장실 된데 아니 ngo스 다 믹다야 중 요레스.
With this assistance to the eye, just an extension of our normal sense, we learn that the moon is a world in space. We learn that the Earth is not the center of the universe, and the evidence is now very strong for that.
그래서 당한주 미기 아니 지가 통야 디그 토라 아니 장실 기 아니 뉴버데 아니 항마 야르 용도 잠발라 아니 간주기 아니 통토비야 세디 아니 자침부스 차제다 다와라도 잠발라 아니 남칼 요베기 아니 딘데기 링 심바치 임바다 디가나시 직된 감그 낭로라 아니 살링디 아니 간주 잠불링 잠마이 발링 심바 망고지 요와 싱그 요레 디 요베기 아니 빵다 아니 슈침부도야 요레스.
If you go out onto a dark night here, when the moon is not full as it is now, you may see 5,000 stars. Galileo, with his telescope, improved on the eye by a factor of 100, but with that factor, he could see hundreds of thousands of stars.
그래서 다이케라 아니 두스마 칠롤 침빈비나 아니 셀라 다와 메베 세몰 남을 때유디 잠발라 찬용부터라 까망아동 라스 통투 레스미기 임비나 아니 타 갈릴레오기 아니 장시 탑 네오디 페주 체제디 답 자스키 아니 파르투 요레스 제자 딜라두 잠발라 아니 케라 남을 통투비 칼미기 장가디 아니 답 자타 망부키 아니 마 통투비 뉴바 차디 요레스.
And so we have just continued Galileo's work. 400 years after Galileo's time, the best images of the sky from the Hubble Space Telescope go not 100 times fainter than the eye, but 100 billion times fainter.
그래서 다 갤릴리오 중에 제가 간주 단다바도 아니 로레스 십자 침브레스 로 십자 침브레스 제자 아니 로 십제기 아니 낭로라 만주 기미기 통토비아 장시기 세디 아니 답 펜봄지기 아니 누바셔 친요레스 다 팅상기 장시 다 제주 된조 리로다나 하븐 텔레스코프레 올라서다.
And since Galileo's time, another revolution in the 20th century, the ability to see beyond the visible spectrum. By opening up the visible spectrum, we have gained another enormous factor in our vision of the universe. Across the electromagnetic spectrum, a factor of 1 trillion in wavelength. Okay. So these are the revolutions of astronomy. And to show it in a picture, here is a graph of the improvement of telescopes' sensitivity over the eye, starting on the left with Galileo and coming on the right to the Hubble Space Telescope. And here is the factor of 100 billion that I talked about. So this is an animation of zooming in on the sky, starting with the view you would see going out at night. This in the southern hemisphere, the Large Magellanic Cloud, a neighbor of the Milky Way galaxy. Zooming in to what you might see with a ground-based telescope, and then the smallest view, the Hubble Space Telescope. And at the end, we've zoomed in 7 orders of magnitude and are looking 100 billion times fainter than the eye can see. We can also use other senses in astronomy, and sometimes converting data for our other senses is a powerful thing to do. Here, for example, is the sound of space of Kepler's harmony of the spheres, the orbits in the solar system. So what you are hearing is the orbits in the solar system, starting with Mercury and moving out, and the orbits are slower, so the sounds are lower. And the tone changes because the orbit is elliptical and it's from our perspective. So this is the sound of space. It's mathematically correct. And the low tone you hear now is massive Jupiter. And scientists can use different sensory data to understand, sensory input to understand their data. This is the sound of the first 10,000 years of the universe, compressed into 6 seconds and raised 50 octaves so you can hear it with your ear. The sound of the Big Bang. So we have also had another revolution, not just the revolution that lets us see much deeper than we can with the naked eye, or see invisible waves of light. We've had a revolution in knowing our place in the universe. For ancient times and for most cultures, the earth was obviously the center of creation, and humans perhaps the pinnacle of creation. We now think that is no longer true. Starting with Copernicus, the earth is displaced in the universe, not only to no longer be the center of the solar system, but to be part of a star system that's typical in a system of 400 billion stars, which itself is typical in a universe of 100 billion galaxies. We've even learned that the stuff we're made of, protons, neutrons, electrons, is not typical of the matter of the universe, which is mostly a mysterious form of dark matter whose nature is not yet understood. So the history of astronomy, in terms of knowing what we know, should induce a little humility because it is displacing us in cosmic importance. The universe has a message for us that you should get over yourself, you're not that important. And also there are many things we still don't know. Science, according to Nobel Prize winner in physics, is what I do when I don't know what I'm doing, which means that we are always working at the edge of knowledge, the place between the things we know and the things we hope to know, the things we understand and the things we hope to understand. So the knowledge is tentative. It is never completely secure. Scientists are always on their toes. Science is discovery, and this in particular is a very creative activity, very difficult to put into a textbook. Knowledge, of course, progresses. At the top we have the periodic table of the ancient Greeks consisting of 4 elements. Although it's a primitive idea, it's the same basis of science, that the complexity of the natural world has simple underpinnings, and we can understand those underpinnings. Of course, flash forward thousands of years, and we have the periodic table. And the pattern of the periodic table was noted and partially understood long before we proved the existence of atoms or understood their structure or nature. So with discovery, we're often working ahead of our theories, working ahead of our ability to understand what we see. Taking this to the modern day, in physics we have a tension between a situation where the microscopic laws of physics are extremely successful in the laboratory. They explain almost everything we can observe in the physics lab. And yet the schema, or the way particles are arranged in a hierarchy, or the way the forces of nature distinguish themselves from each other, is not understood. There is a theory, so-called standard model of particle physics, that accommodates this scheme, but there is a lack of deep understanding for this scheme. So the theory is not complete. The journey is not finished. To give an example of a great success of the last century of science, we have a microscopic theory involving molecules that can replicate and transmit information, which led to the awareness of the genetic code. This powerful revolution in biology is still being played out, but in its basic form, it leads us to understand the diversity of the natural world, things we've seen and admired and wondered about for centuries. But there are still some profound mysteries. Even though we have a microscopic knowledge of some of the components of the brain and routinely measure these and make correlations between these components of the brain and things that can happen with a human being in behavior and thought, we're far from a complete understanding. If you think of the amazingness of consciousness, and I don't just mean the fact that we are all sentient beings, but the fact that inside our heads we have a little movie playing of our lives as we experience it. And we are aware that there's a movie in our heads. So we are both the observer and the director of this little movie playing in our heads that's consciousness. This is not understood. There's even an argument deep into the science process over whether things in science are actually invented or discovered. The classic stereotype of science is that science is deconstruction. It's reductionism. And in fact, that can be one of its biggest failings. That science, to use a metaphor, is taking the rainbow apart. Whereas art, for example, is putting the rainbow together, combining colors in different ways for delight and amazement. But the truth is not so simple. The distance between the artist and the scientist not so great. I'll use the example of Michelangelo. When he was asked how he produced his amazing sculptures, he did not say that he took a block of marble and imposed his will on it, his artistic vision. He said he went to the marble quarry at Carrara and he found marble where within was a form waiting to be liberated. To Michelangelo, he discovered his art. He didn't invent it. So is science invention or discovery? Is mathematics invented or discovered? People will argue these for a long time with no definite conclusion. But imagination is an important part of science. And it's the delight in combining things in the natural world or producing a theory that explains something that was a complete puzzle. And as I prefer to do in this talk, I will sometimes use my examples from art rather than science, because I think the inspiration and the thought process can be very similar. In this simple piece from Picasso, two disparate parts of a rusty bicycle are combined to make something wonderful and new, the head of a bull. And in a sense, there's a discovery analogy with what scientists do. When they take pieces of mathematics, when they invent theories that explain a wide range of phenomena that hitherto had seen as being unconnected, disparate. Imagining the impossible is a powerful skill for scientists to have. I'll use an audible version of this. The music, which gradually slows down, is from a piece designed for the player piano to play at 300 notes per second at the beginning. No human can play this. Does that mean it isn't music? It's impossible. You're imagining the impossible, but that doesn't necessarily make it non-musical. Scientists imagine the impossible all the time, knowing that sometimes the impossible may happen and they may discover it. Here, for example, on the upper left, is Newton's imagination of orbits 350 years before we had the technology to travel in space, because he had a theory that could explain how we would eventually do it. And now in modern astronomy, we've discovered Earth-like worlds on which we should not be surprised if there are sentient beings, should we have the technology to discover them. Meanwhile, science fiction writers and people have been imagining these worlds, visualizing them, telling stories about them, drawing pictures of them for decades, anticipating the science that's still to come. Science, of course, is about reasoning and logic. And there can be failures of logic. There can be situations where we overreach. But remember the quote of the Nobel Prize winner: "Research is what I do when I don't know what I'm doing." It is important to be at the edge of your knowledge, because if you are safe in your harbor or not far along the tree branch, you're not exploring a new terrain. You're not contributing to new information or new knowledge. So you have to be willing to break the system. You have to be willing to break the theory. You have to be willing to gather data that is uncomfortable because it challenges the wisdom. There are underpinnings of science that are so deep and profound that we barely question them, but we should. For example, science and life itself would make little sense if there were not cause and effect. Without even thinking about it in the everyday world, we believe that things happen for a reason, and we look for that reason, and scientists make it their life to look for that reason. And in fact, if you try to imagine it, the world or the universe without causality would be a very strange, confusing, and scary place. On the other hand, if you push cause and effect too far, you end up with determinism. You end up with the idea of Newton's clockwork universe, where the universe is a machine. And in that, as the philosophers pointed out in Newton's time, you have a problem with free will. How do we decide what it is that we do? How do we have the creative power of thought? How do we have the ability to do anything that we think we can? So there's a tension between the strong causality premise of science and the fact that determinism really has no place in modern theory. Because another fundamental attribute of science, which sounds like a bug in software terms, but it's actually a feature, is uncertainty. Science is uncertain in three conceptually different ways. One is conceptual. One way to make a mistake in science, or to fall off the scientific method, is to make a false premise, to confuse a correlation with a causation, to infer a pattern where none is present. Remember, the heart of science is the curiosity that leads us to look for patterns in the natural world. But of course, we are too good at this. We are too good at this because we had to be good at this. When we were hunter-gatherers tens of thousands of years ago, if you were out there on the savannah in Africa and you saw something moving in the grass, you thought it was a tiger maybe, and you were scared. It's good to think that it's a tiger and be scared, because then you may save your life. But if you don't notice the pattern, then you may be lunch. So we are wired to look for patterns, to overinterpret patterns, and it can be a problem in science. At the macroscopic level, there's no such thing as perfect data. Scientists are always trying to improve their instruments, going from Galileo's humble spyglass to the Hubble Space Telescope. They're trying to gather more data. Scientists are insatiable in their quest for data. And then at the microscopic level, a startling discovery of the last century, there's a fundamental limit to the precision with which we can know the natural world from quantum theory. Despite the objections of philosophers and some of the physicists, including Einstein, there is no way around this limitation. We believe the natural world has built-in limits to what we can know, and that, in turn, should induce a little humility. So we need more data, always. We gather data, and we wonder if X and Y, two things we measure, are related, and maybe we think they're not, and maybe we gather more data and think they are related. We can make a model, a hypothesis, and then a theory to explain that data. It's how science works, after all. And then we extend the range of our observation, and maybe it's not as simple a relationship as we thought. Maybe the diagram, instead of a straight line through the data points, is a curve. So this is why, in a nutshell, we gather more data all the time. But we can be confused, as I mentioned, by making a false premise. Here's a beautiful correlation between, measured in different parts of the world, the global average temperature and the number of pirates present. So does temperature make more pirates? Is piracy caused by being too hot? No. The underlying variable here is time. And so it is fairly simple to make false causation. And that is probably the biggest enemy in science. We also have to acknowledge that in our quest for perfect data, we are doomed to fail, because statistics play a powerful role. That can be in terms of limited amounts of data, where you don't have a good sample. A roll of one dice will never tell you the statistics of a dice. You must roll it many times. And at the microscopic level, the indeterminacy is profound and fundamental. It is impossible to predict when any single radioactive atom will decay. Impossible. And yet, a collection of those atoms will decay in an entirely predictable statistical fashion. So we must live with both aspects of this. We need evidence, obviously. Science is based on evidence. It must be communicable to others, not just to ourselves or in our heads, and therefore reproducible. It must be quantitative, conveyed in numbers, not just words. It must be not a matter of opinion. People must agree on this in an objective way. And of course, the evidence is never perfect. So we make assertions in science based on data, and we try and verify them. And in the scheme of science, getting more data is good. Repeating the experiment is even better. And having someone else do the experiment is best of all. For example, here in this mosaic, you see pictures of Saturn from the first 50 years of the telescope. So each of those little images is a drawing, because there were no photographs, of Saturn as seen by someone's small telescope early in the history of telescopes, and they all are different. So if you ask back then, 1660, which of these is the way Saturn really looks, there is no answer to that question. Does Saturn have two moons? Does it have rings? Is Saturn an elliptical object? You can't tell. Science is always at the limit of observation. You always want better data. Well, in this instance, we've come far. This, from 3 weeks ago, is a mosaic from the Cassini mission. We have sent our robots to Saturn and taken beautiful images like this of the system. And so we know what Saturn looks like. But in 1660, you do the best you can with the tools you have. And maybe eventually we will have even better pictures than this. So in astronomy, for example, we're in a situation where our direct evidence of exploration is extremely limited. In the history of technology, humans have only stood on one other object than the Earth, and it's the moon. And it was almost 50 years ago. We have remote sensing, or robots and cameras, that we've sent about 1 billion miles from the Earth into the outer solar system. And so that's pretty good data, as you saw from the picture of Saturn. And then occasionally we get lucky and we get free samples of the outer solar system that land on Earth, in this case a meteorite, and they may have come from 10 billion miles away. But 10 billion miles in the size of the universe is nothing. The size of the solar system reduced to a grain of sand means the nearest star is not even in India in a scale model. So we have no direct evidence of all the stars and galaxies in the universe. For a huge percentage of the universe, basically 100% of the universe, our information is completely indirect and based on radiation. In talking about the things that science is, I think it's important to talk about the things that science is not.
Senrik di kari ime kejasia kechimbu imanashi ani kari ani senrik mare di kejasia kechimbu chag yores.
So here I'm going to read from a summary of how science works from the National Academy of Sciences of the United States. That is the most esteemed group of scientists in the United States.
Chazada dela to khashish ma loya yus chazada di tanda ari knanglo la ani chigam senrik da dewe ke ani sokba ani ta che toshu di ke ta nanglo la tembe yewe ke ne du chag yores.
And the three positive statements are familiar to you. Scientists pose, test, and revise hypotheses to explain the natural world is one.
Chaza di nanglo ne jusum ani dingon kiram su junga yo cha di yores ani di khares labin bena ani senrik ba chu ki ani rangjung kin khuryu nanglo la ani thangbung la toship che ki da toship de la debe ke cheba che ya ani cheba de dig mindu ani dig du mindu ani takje che ya din jusum chigres.
Two, scientists only use natural causes to explain natural observations, so there is no appeal to supernatural phenomena or gods or goblins or ghosts.
Chaza da di ne ju chigres ne ju niwa di khares labin bena ane rangjung ki khuryu nanglo la toship khari chungbi ki nezu dinsun deshi gaya la ane rangjung ki ane jujen la ten ane deshi gayri ma do dile gewe ki la da de da ane dinde ki ane ta deshi gyadan chik la kyap ju mares.
And third, that science claims in science are subject to peer review and replication. And so in science, it doesn't matter how smart you are. If your observations don't agree with someone else's, or they are not part of the community of observations, then they will fail.
그래서 다 세리기 아니 낭로라 아니 계자 가르시베면나 아니 남샤 가르시베면나 된조 상마 아니 세리기 속된 낭로 여베긴 세리기 심바츠기 아니 결십 지야다 아니 딜라 주와당기레스 제자 딜라도 삼발라 아니 계란직 세리기 낭로라 릭바 요왔다 칸디스 임베나 아니 계란 시와 샤와 된조 아니 세리기 속된 낭로라 아니 뇌레 메비임베나 계란 시와 샤와 된조 아니 타주 마레스.
But here are the three things that science is not, and they are just as important, and I think especially in my country, with younger people, people are not aware of this aspect of science.
그래서 디 제라 니주 숨시에 요레스 제가 디 카레스라나 아니 세리 마임베키 니주 숨시에 요레스 제가 디야 개침부차 요레스 제가 다 니기 롱발레 요베키 아니 다 로슌슌 딘주 임빈베나 디 니주 숨디 아니 고 세리 마임바디 시라시다야 카세오 요마레스 고수민두스.
Science does not claim proof. Science is always a work in progress.
세리 가두임베나 콩제 지기요 마레스 콩제제 지기 마레스 세리 세야디 카레스라베메나 가두임베나 아니 고 열겐 로데야지레스.
Science is not democratic, and it is not dogmatic.
제가 아니 세리 세야디 아니 망주 글람니 탁주 제기 니주지 마레스 드가 나시 아니 세리 세야디 아니 룽다 아니 깔레 땡제 탁주 제야지 마레스.
And third, science is a human endeavor, but it cannot make moral or ethical decisions.
제가 아니 숨바디 카레스라메나 제가 아니 세리 세야디 아니 로 미키 아니 자와지 차디요레스 레가지 차디요레스 임베나 아니 세리기 아니 랑도르다 드가 나신 찍다 제주다 데베키 에스테틱 라이도 주제 라이나레 제주라 데단 데베키 아니 네주 가야 탁주 지기 마레스.
And this last one, I will of course comment, is very important to us because we know that a byproduct of science has been things that are quite dangerous, nuclear and chemical weapons, the possibility to degrade the environment, pathogens that could harm us.
그래서 단 니숨네 네주 타마데 베차시나 다지 랑도르다 아니 제주톨 탁주 지기 마레스야 니콜랑이 데시스 야빈베나 아니 계신부 자기 요레스 가진 라빈베나 아니 세리기 아니 생릭레 중외기 아니 좀리기다 주릭다 된솔레 땡시 아니 베샤시나 지가 춘자수야다 아니 고류라 노준시야 대가나시 지 간솔라 뇌진이기 아니 nemburik 망모직 중야기 디 강이 스테디요레스.
Scientists must engage in this debate. It is not sufficient to say, I am doing my work, somebody else can worry about this.
제가 딜라도 잠발라 생릭 버츠기 아니 니 생릭 나랑 생릭이 내가 지기요스 제가 딜레 중외게 강에 된서 미신베기 주도레스야 디 시에는 디기요 마레스 제가 네주 디토라 아니 생릭 버츠기 아니 냠슈 트메치고요레스.
But the society cannot say, these scientists are doing terrible things, we should stop them. Society has to take responsibility, which means education.
제가 임베나 아니 미망 저기 야메나 지조기 아니 생릭 버츠기 내가 가르치기 요아디 아니 까투 마레스 임베나 아니 수수기 아니 랭겐 드롭토비아 랭겐 빙고체 와치야디 계신 보체기로 제가 딜라도 잠발라 키엔 룹준스야디 계신 보체기요레스.
The last ingredient of science, because we live in the information age, is information. And I want to give you a sense of the dramatic progress, the inundation, if you like, of information. How do we define information? We think it's something that computer scientists understand, but actually it's very simple. If you have a piece of paper and you draw a dot on the piece of paper, you want to know where the dot is, you can define it by dividing the paper in half and saying is high or low, and then to the side, it's one side or the other. Each time you divide the piece of paper is one bit of information. And so by successive divisions, you could define the dot down to the level of one atom if you wanted. And these bits of information, is it high, is it low, is it loud, is it soft, is it bright, is it dark, is it 1, is it 0? That's the basis of the information age. Everything in your phone, in your digital life, is information like this, simple. The basis is simple. So let us put numbers on the information in our world. The information, of course, that science has mostly given us, but which we're responsible for digesting or understanding. So I now use the computer terminology of bytes, where 1 byte is 8 bits. And you can see the equivalent here. At the top you have a kilobyte, how much a page of text is, a novel, which is 1,000 times larger maybe, and all the words ever spoken, the second bottom, which is an amazing number of bytes at 10 to the power 19, a 1 with 19 zeros. But, so imagine the digital equivalent of all the words every human has ever spoken. It's a lot of words, it's a lot of conversations, a lot of information. Well, all the new information in the world this year is 100 times more than that. Just the new information in the world. That's what we're dealing with. And I can put the history of information in a graph, which actually goes back to the Big Bang. And in fact, really starts with the Earth. So we can define life as digital information. James Watson, co-discoverer of DNA, actually said that. Life is digital information. And so if we use the equivalent information coded in a biological organism and watch how that has evolved over the history of the Earth, it's a rather slow progression. And there are 2 enormous revolutions in the rate of information gained on our planet. One, of course, was Gutenberg, the movable press, the first books to be transmitted and reproduced. And that increased the rate of information of human culture by a factor of 10 trillion from what came before, oral history, oral tradition. And then the digital revolution, the one we're still living through, increases that rate of information by another factor of 1 billion, which is a phenomenal amount. And in science and technology, we're projecting to extraordinary situations where computers could indeed have the capacity in information terms of the human brain in only a couple of decades. And that will face us with another huge set of ethical and moral decisions as we approach the possibility of machine intelligence. So these are things that are facing us, and it is the success of science and technology that has led to this. But to finish, let me drop back to the mystery of science and the beauty of science and acquaint you with one of my favorite places where I do some of my observing, telescopes in Hawaii, Mauna Kea, and a montage of the night sky. But before I do that, make one comment on theory, which I haven't talked much about. If we imagine the role of theory is to explain everything that is in the universe, and then none of the things that are not, and we are modest or humble, we imagine our current theory explains some fraction of all the things that happen or exist in the universe. And our goal is the dotted line, a theory of everything. But it's very tricky to know the things that do and don't exist in the universe when you've explored so little, when your science is so young. And so how, in practice, are we going to know whether or not we have a theory of too much? So the whole issue of theory, of the profound understanding of the universe, of knowing that you know everything, is really not something I think we can be confident of. And here's a more positive way to put this. You imagine the universe is composed of things that are and things that aren't. There are also things that are possible but don't happen. Things where the probability is so low that it won't happen in the history of the universe, but it doesn't break a law of physics. There's a lot of those things. And then there's another piece. It's the piece in here. It's our minds, the things we can imagine. And the trick of science and the beauty of science and the challenge of science is that we can imagine maybe not even all the things that actually happen in the universe. So I don't have the imagination including everything that is. We can imagine many things that are possible but don't happen. And we can imagine things that are impossible too. And they are all part of one piece of cloth for us. We don't have to make a distinction, nor should we. In science, we have to. But in our brains, in our imagination, in our creation, we don't have to make that division. And I kind of like that. Thank you.
Thank you very much, Chris. I think that really gives a good overview of the history of knowing, and not only what we know, but what we don't know, and ways that science uses to find out what we don't know. I know from listening in on your classroom the past 2 weeks with the geishis that they have many, many questions. And we'll have time for just 1 or 2 questions. There'll be plenty of time after lunch for further questions, but I'd like you to ask some questions now for Chris, 1 or 2 questions. We'll start here.
anda 체릭베 아니 셰도다 사르니 사르데젤 중에 중대카 긴가도 뉴주기 직딩기 견도 용라야 니 가서 그래 펜데체도 줄발레 니 뇌제기랑 신전의 미주르베 체도 세리바랑은이래 니 두와 지 이래 소변나야 이제 지용이디 뉴주미 유베 체도 두개다 탑람 가릴 땡고를 탑람다 개체쇼.
So there has been a lot of discoveries and inventions in the science, and so in order not to become a kind of a source of problem for the society, what methods we should adopt to make a good use of these discoveries and inventions?
It's a very important question, and I don't have a perfect answer, but you know, I am an educator, and to me it starts with education. When I look at the bad policy from governments or politicians, when I look at statements from responsible people in the society that are erroneous, that clearly don't understand the science, I just feel that we need more education. So when people are dealing with issues of the climate change, for example, is a really good example, where the scientific community has a consensus at the 99% level, which is very rare in science for scientists to agree at that level on any one issue. And yet in some countries, like the United States, there is a complete division in what the public believes on the issue. Then that is a problem. That's actually a limitation on action at that point. So I think that that's the heart of a problem that applies in other areas. Genetic engineering would be another example, because people don't truly understand what it means to alter the biology of ourselves and what's possible, what can be done, what should be done. So I just go back to education always.
동방이 게라라 참루트동 저기 토네 니들이 제자도 저기 토네 저거 전디 송송 다다 게라가 자동 정시고 뭐 송송 대인데 자동 주세의 템버 주동 하경이 내도 소모 용좀 봐 사부 시동 쉬어야 돼 얘네 계좌 칭보 코랑기 이종사가 자와대 자동 정시고 마통비 진세 가르세와당 자동 계좌 칭보 대 용사게 뽕다 조 가르여야 쉬어요.
In your presentation, you have talked a lot about telescopes and discoveries made by these telescopes. And by this use of these telescopes, you can go back to billions of years in the history of the universe. But what is the reason why you cannot detect the Big Bang itself by using telescopes? Why is this limitation?
So for going back, we can go back with reliable techniques to physics that is understood in the laboratory to a microsecond after the Big Bang, 1/1,000,000th of a second. That is conventional, tested science. And that's pretty impressive. So, you know, you could just be happy with that. As for going back further, the simple answer is because the universe in that early state, the information is sort of obliterated by extreme temperature, density. It's chaotic, it's disorganized. So there's very little for us to directly observe. And then another important point that's about how science works is, and people forget, is that the Big Bang theory, a very well-tested theory, is a physical description of what happens from a situation of extremely high temperature and density. The Big Bang theory is not an explanation for why the universe exists, for what caused the Big Bang. I mean, some people might like to speculate, but they are not doing science, conventional science, when they do so. So science is also accepting the limitation of your theory, and the limitation of the Big Bang theory is just what I said, that it doesn't answer some of the questions you might naturally want to ask.